In this episode, we focus on a subtle but critical auditing challenge: evidence integrity when the system you are auditing changes over time. For brand new learners, evidence can feel like a snapshot, as if you collect a log, a configuration file, or a model version record, and you are done. In AI environments, that mindset can mislead you because models can be updated, prompts can be adjusted, data sources can be refreshed, and retrieval indexes can be rebuilt, sometimes frequently. If evidence changes underneath you, then an audit conclusion based on yesterday's artifacts may be wrong today, and a finding that seems clear may become hard to prove if the trail is not preserved. Evidence integrity means the evidence is authentic, complete, and protected from tampering, and it also means you can show what was true at a specific time. Domain 3C expects you to understand how to validate that integrity so your audit results remain defensible even when the system evolves. By the end of this lesson, you should be able to explain how time and change affect evidence, what threats to integrity look like, and what practical methods auditors use to keep evidence trustworthy. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A useful starting point is to understand why AI systems are especially vulnerable to evidence drift compared to many traditional systems. Traditional applications change too, but AI systems often have more moving parts that can affect behavior without changing the underlying infrastructure. A model version change can alter outputs. A prompt template change can alter rules and tone. A retrieval scope change can alter what data becomes reachable. A data refresh can alter the knowledge base or the distribution of training data, which can shift behavior even when the model file stays the same. This means the same user question can yield different answers on different days, and the audit must be able to explain which system state produced which behavior. Evidence integrity, therefore, includes preserving the state of the system at the time evidence was generated, so you can reconstruct what happened. Beginners sometimes assume that if the organization provides current settings, that proves what was true during the period under audit. In reality, current settings may hide historical risk because a risky configuration might have existed earlier and been corrected only after an issue was noticed. Auditors must therefore treat time as a core dimension of evidence integrity, not an optional detail. The first concept to hold is the idea of an evidence timeline, which is a structured way of linking evidence to time windows. An audit typically defines a period under review, and evidence integrity means you can show that the evidence you collected actually corresponds to that period. Logs are naturally time-stamped, but configurations and artifacts may not be, unless versioning is used. So the auditor needs to create a timeline that includes key changes, such as model deployments, prompt updates, connector changes, and policy modifications, then anchor evidence to the correct intervals. For example, if you are evaluating whether retrieval access was appropriately restricted, you need to know whether the retrieval configuration changed during the period and which configuration was active when specific log events occurred. If you are evaluating incident response readiness, you need to know which playbooks and monitoring rules were active when an incident was detected. Building a timeline is not extra paperwork. It is how you prevent evidence from being mixed across states. For beginners, it helps to think of the system as having versions, like chapters in a book, and you must know which chapter you are reading when you interpret a specific event. A major threat to evidence integrity is incomplete or inconsistent versioning of key AI artifacts. In a mature environment, model versions are tracked in a registry, prompt templates are stored with version control, retrieval configuration changes are recorded, and deployments are linked to version identifiers. In a less mature environment, teams may edit prompts directly in a console, update retrieval sources informally, or deploy model changes without consistent identifiers. When versioning is weak, the auditor cannot confidently prove what configuration produced a given outcome. That creates risk for the organization too, because it becomes difficult to diagnose incidents and to demonstrate compliance. As an auditor, you validate integrity by checking whether artifacts have stable identifiers, whether changes are recorded with timestamps and owners, and whether deployments can be traced to specific artifact versions. You also check whether environments are separated so development changes do not leak into production evidence. Beginners should recognize that versioning is not only a developer convenience, it is an evidence integrity control. Without it, system reality becomes hard to prove, and that undermines both audit confidence and operational resilience. Log integrity is another foundational concern, because logs are often treated as the primary source of truth for what happened. Log integrity has two sides: whether logs are complete and whether they are protected from alteration. Completeness means logs include key events, such as model requests, policy decisions, retrieval actions, tool calls, and configuration changes, and that these logs are retained long enough for the audit period. If logs are missing, rotated too quickly, or captured only at a high level, they may not support audit conclusions. Protection means logs are stored in a way that makes tampering difficult, such as restricted access, immutable storage patterns, or centralized systems with strong controls. In AI systems, log integrity also includes correlation, because you often need to tie a model request to retrieval and tool activity through shared identifiers. If correlation is weak, a malicious actor could perform actions that are hard to attribute, or an auditor could misinterpret a retrieval event as unrelated. Validating log integrity, therefore, includes reviewing logging configurations, retention policies, access controls for logs, and the presence of consistent identifiers. For beginners, the key is that logs are evidence only when they are trustworthy and complete. Evidence integrity also includes the integrity of data lineage records, which can be fragile when data changes frequently. Training datasets may be refreshed, evaluation datasets may be updated, and retrieval indexes may be rebuilt as new documents enter the system. If lineage is not preserved, an organization may be unable to show what data was used to train or fine-tune a model version, or what documents were available to retrieval at a specific time. That matters because bias and performance issues may be tied to changes in data composition, and privacy or licensing obligations may be tied to particular sources. Validating lineage integrity means checking that datasets have identifiers, that changes to datasets are recorded, that the organization can reproduce or at least describe the dataset state used for a given training run, and that approvals for data inclusion are tracked. For retrieval systems, it means being able to show which repositories were connected and what document sets were indexed during the period. Beginners often assume data is static because it sits in storage, but AI data is often curated and transformed repeatedly, and that transformation chain must be auditable if you want integrity. A concept that helps tie these ideas together is chain of custody, which is the discipline of knowing who handled evidence, when, and how it was preserved. Chain of custody is often discussed in forensic contexts, but the idea applies broadly to audits where evidence might be contested. If a finding is serious, stakeholders may ask whether the evidence was altered, whether it came from the correct environment, and whether it truly reflects what happened. Chain of custody practices include recording where evidence was collected from, recording timestamps, preserving original copies, limiting who can access evidence, and maintaining a clear trail of any transformations like redaction. In AI audits, chain of custody matters because evidence may include prompts and outputs that contain sensitive information, and because artifacts like prompts and configurations might be easy to edit. An auditor validates integrity by ensuring evidence collection is repeatable and documented. Beginners should understand that chain of custody is not about suspicion, it is about defensibility. It allows the audit to stand up to scrutiny and prevents the organization from dismissing findings due to process uncertainty. Another challenge unique to AI is that model outputs themselves can be unreliable as evidence unless they are tied to system state. If you capture an output today and use it to argue that the model behaves a certain way, someone can argue that behavior changed after a model update or that the prompt context differs. That is why output evidence should be accompanied by metadata that describes the conditions under which the output was generated. Useful metadata includes model version, system prompt version, retrieval configuration version, any policy settings, and the timestamp. For systems that use retrieval, it is also important to capture which documents were used, because that can explain why an output contains certain information. This makes outputs usable as evidence because they become part of a trace, not isolated text. Without metadata, Outputs are like photographs with no date and no location. They may still be interesting, but they are easier to dispute. Auditors validate evidence integrity by insisting that behavior-based evidence includes the context needed for reproducibility or at least for defensible explanation. Change records are central to evidence integrity because they provide the bridge between states, and validating them involves more than checking that a ticket exists. You want to see that changes are linked to artifacts and deployments, that approvals match the risk, and that emergency changes are documented and later reviewed. You also want to see that changes that affect behavior, such as prompt updates and connector modifications, are treated as security relevant, not as casual edits. Evidence integrity suffers when teams make changes outside the formal process, such as editing prompts directly in production or enabling a connector as a quick experiment. Auditors validate integrity by looking for consistency between change records and observed system state. For example, if an artifact version changed but there is no corresponding change record, that is an integrity concern. If logs show a configuration change event that is not documented, that is also an integrity concern. Beginners should recognize that integrity is often revealed by mismatches between evidence sources. When evidence lines up, confidence increases. When evidence conflicts, you have to investigate and document why. Time synchronization is another practical detail that can quietly undermine evidence integrity, especially when systems span multiple services and vendors. If timestamps are inconsistent across logs, it becomes difficult to correlate events accurately, and an attacker might exploit this confusion. In AI systems with multiple components, you may have application logs, model service logs, retrieval logs, and identity logs, possibly in different systems. If those systems use different time settings or inconsistent time zones, traces can appear out of order and incident timelines become unreliable. Auditors validate integrity by checking whether systems use consistent time standards, whether logs include time zone information, and whether correlation identifiers exist to reduce reliance on timestamps alone. Beginners should understand that time is part of integrity. An event that cannot be placed reliably in sequence is harder to interpret and easier to dispute. This is why organizations treat consistent timekeeping as an operational control, not just a technical detail. As you build your audit approach, it helps to think about integrity validation as both preventive and detective. Preventive integrity controls include immutable logging, strong version control for artifacts, strict access control for configuration changes, and formal change management. Detective integrity controls include periodic reviews for undocumented changes, monitoring for unusual access to evidence repositories, and reconciliation between different evidence sources to detect gaps. An auditor can test both by examining how evidence is stored, who can modify it, and whether the organization has methods to detect when evidence might be incomplete or altered. In AI contexts, detective controls are especially important because system evolution is fast, and even well-intentioned teams can create gaps by moving quickly. Validating integrity means confirming the organization can produce a coherent story of what happened and why, supported by evidence that aligns across logs, lineage, artifacts, and change records. If they cannot, the audit should treat that as a risk because it reduces the organization's ability to manage incidents, demonstrate compliance, and learn from failures. As we wrap up, remember that validating evidence integrity in AI audits is about making time and change explicit rather than letting them blur your conclusions. You build an evidence timeline so each artifact and configuration is tied to the correct period. You examine versioning to ensure models, prompts, and connectors have stable identifiers and traceable histories. You validate log integrity by checking completeness, protection, retention, and correlation across components. You validate lineage integrity by ensuring datasets and indexes can be traced and that transformations are recorded. You preserve chain of custody so evidence remains defensible, especially for high-impact findings. You treat model outputs as evidence only when they include metadata that ties them to system state. You reconcile change records with observed state to detect undocumented changes, and you ensure time synchronization so event sequences can be trusted. When you can do these things, you can audit AI systems that evolve rapidly while still producing conclusions that are clear, defensible, and grounded in trustworthy evidence.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.